Hello, everybody can hear, right? So let's start. Okay. Today we are going to continue to study the digital control part. Okay, as I said, digital control is almost everywhere, and in another word, there's a word to say that it's called ubiquitous. How many of you used this one before? Ubiquitous. Digital is everywhere, including the control. Digital control is ubiquitous. Okay, but we really need to learn all the basics. Last time we talked about differential equation, z transfer. So we said that if you can do scalar type of a first order differential equation, remember you have a k also changing here. It's no longer a constant. So then this is a general form of first order differential equation. So this is actually can be derived from the room temperature control once you discretize it. So remember, behind this one, there is a continuous time differential equation. Then we have this one by a process called discretization. Discretization. So in that sense, the y dot t is approximately equals to y k t minus y k minus 1 t divided by the sampling time ts. Okay. Here we're using a small letter ts. Okay.
Professor, we can't see your screen.
Oh, really? Give me a second. So I'm sorry. Thank you for telling me. Let me see. What's the basic idea here is to show you the screen. Okay. Can you guys see now? Let me start. I said digital control is ubiquitous, right? So that word is was not in my dictionary until in the recent 15 years I learned this word, ubiquitous. So this is a scalar form of a general and first order differential equation. And this one is actually derived from a first order continuous time differential equation, first order. Okay, continuous time differential equation. Then through a discretization idea by using a finite difference. So if your sampling period is small enough, this is approximately the same as y dot. Then put there, you are getting a difference equation. And this difference equation, u can be anything, u of k. It's not necessarily constant. So then this one is actually this general form of first order, okay? So then we can do iteration, solve the first order difference equation. And this is called brute force recursive. You just derive from 0, okay? But in the end, you can see this xk is linked to the external driving function, driving control. This is the initial condition. So this is the initial response, okay, due to the initial condition. So this is called zi, okay? If you don't have a 0 input, that means 0 input. If you don't have an input here, then everything output is linked to the initial condition. And this part actually is called ZS, zero state. So meaning when your initial state is 0, when x0 is 0, then the other response is all because of the control. And remember, there's some interesting thing here, alpha j and kj. So these two indices adding together will give you k minus 1. So there's some rules in there. So it's just condensed notation of this. So you can derive this one in a brute force way. But what if you have a second order? So you can see this k plus 1, k and k minus 1. So this is already second order, okay? You can write a second order differential equation in terms of first order differential equation in vector form, okay? Vector form. So here xk vector is this, and then you can write the familiar format. So this is like the state space equation we wrote, like x dot is ax plus bu, and y is cx plus du. But in reality, this term is usually 0, okay? Du term is 0. So then after discretization, this becomes phi. This is a constant. This is a matrices, okay? Matrices. So this is the same thing as a scalar format, the first order. So you can use the same thing. You can write like this, okay? But everything here is just matrix. So this is H matrix, X equals phi k x0. Then this is, you can see k minus 1 minus j plus j will be k minus plus 1. So that's the rule. There's a way to do that. So this is, let's say this is some sort of mechanic. Meaning by programming, although it looks very complicated, by programming you can do mechanical way or robotic way to get this one solved. So we do need some framework, like we use Laplace transform to solve differential equations. Here we need a Z transform to solve differential equation. So we already, so this is a continuous time domain. We solve everything, leaving everything is in the S. So this is also S, okay? We have learned this thing already. So that's continuous time, okay? This is a continuous time system, okay? Continuous time system. But in discrete time, we need something called a Z transform. That is, remember, k goes to minus infinity here, okay? But in our real life, we don't have to. Because usually, when it is less than 0, everything is 0. Say, for example, I have a step function like that. So what's the Laplace transform? I showed you is, so this one should be greater. Okay, something wrong here. I showed you last time. So this is basically is written as 1 minus something like this, right? So, and there is also something like 1 over z to the power of n plus 1, and send n to infinity, then this is 0. So to make sure this is less than 0, then this z should be greater than 0, okay? This is called region of convergence. ROC, region of convergence. So in other words, if you do, I give you a sequence, okay, then get its x of z. So this is called x of z. So which is a Laplace transformation pair of x of k, okay? While x of k is given like that. So this is called the Z transformation pair, okay? Z transformation pair, okay? It's a pair, okay? Just like we say 1 and 1 of S is Laplace transformation pair, right? Let's not say 1 times UT, okay? It's a step. So this one is also everything is 0, and then you have decaying, or you have 0, or you have exponential. So this one is the same idea. You lumped this one with A divided by Z, to the power of k minus k, then you have the same idea. No, it's k, it's not minus k, is k. Okay, something like this. So then you end up with 1 minus a divided by z. Then you also have a divided by z to the power of n plus 1. If this one goes to 0 when n goes to infinity. Okay, when n goes to infinity. Okay, so again, this is wrong. It should be greater than a, so that this guy is less than 1. So that anything less than 1 to the power of infinity is 0. So then you basically have this one left, and this one will give you this. So that's where we stopped last time. Okay, we're moving on today to see more cases, and we're going to establish a concept that if you have a discrete sequence, so these are the discrete sequences, okay, then there exists x of z, okay, x of z, according to this definition. So let me show you another example. So this is called the ramp function, is like this. So in continuous counterpart is x of t is t, okay, is t. So which is xk is k, so you have 0 in here. So basically you end up with this one here, and it may happen that this is non-trivial for you to do the proof. So how to prove that? How to prove that? So I hope you will find a way to prove it, okay? Find a way to prove it. So, but the final solution is convergent. Then this z divided by z. So remember, this one is t is, remember this? Okay. So now we're saying that k sequence will proportional to z 1 minus, oh, sorry. Wait a minute. It's z minus 1 square. But do you think we can also write this thing as z minus 1, 1 minus z minus 1 square? Yes or no? Yeah, you divide it by z square, both numerator, denominator, you'll get this. Okay, so this is the same, okay? This one and this one are the same. But let me remind you, this is a Laplace transformation pair in continuous time, discrete time, okay? But remember, we did the continuous time, one is 1 of s, discrete time, like discrete time constant is z minus 1, okay? Z minus 1. That gives some hint. You have z minus 1 square, okay? Z minus 1 square. So what is the inversion? Again, you use this type of inversion is usually very complicated. So we are not going to do this. So we usually will give a Z transformation table. Z transform table. So we usually use a lookup table, LUT lookup table. Then to use the lookup table, you probably will bring the x of z into a format that, remember, we did something called PFE, okay? PFE, partial fraction expansion. Then you do this, then you can, we're going to have an example after this, okay? So we just learned a Z transform giving xk, how you get this, and similarly, giving xz, how to get this is the inverse z transform. So let's do, this is a PFE, okay? This is a PFE. So this is a PSE, called power series expansion. So basically it's called long division method. So say for example, you are giving FZ, can you give me FK, draw, what is this one? So the idea is simple. So you put this one as a numerator, this one as denominator. So what you are going to do is you have 1 minus, so you have a, okay. So if you put a 1 in here, okay, so you are going to have 1 minus z minus 1 plus z minus 2. So this one times this one, you will get this one. Then you do this minus, okay, so this 0, this one will give you z minus 1. And this one you give z minus 2. Do you see that? Then, excuse me. Because this is a minus z minus 1, to make that one happen, so 1 plus this one. So minus, so you got a minus z minus 1. This is times this one is positive z minus 2. Then this is minus z minus 3. Then you do the minuses here. So you cancel out this term is 0. Then you have this one minus this one. Oh, wait a minute. So it's minus 2. So this is a minus. So this is a minus. So you are going to, this is a plus. Okay. So you are going to have minus 2z minus 2. Then you have plus z minus 3. Because this is a 2, 0, 2 z minus 2. So here you get another term is 2z minus 2. So you put it here, this guy times this guy is minus 2z minus 2. But here you got a positive 2z minus 3. Do you see what I'm doing? Then what I'm going to get is minus 2z minus 4 is minus 2z minus 4. I don't have space in here, okay? Let's continue. Then you do this one minus is 0. This guy minus this guy is going to minus z minus 3, right? Because 1 minus 2 is minus 1. So here is a 0 minus 2 is plus 2, z minus 4, okay? So this is minus z minus 3. So then you can know that this is minus 1, z minus 3. So you keep doing this one. This one will give you fk, okay, fk. So in other words, what is fk? So this is a k. Then it's simply writing according to the definition. The fk when k is 0 is 1, okay? So if when k is 1, that is minus 1. So you have minus 1 here. So the second point, the first point, when k is 2 here. So then you have minus 2 roughly here. Then you have k is 3 is minus 1 again. So it's something like this. Great, give me a second. So it's something like this. So, and maybe you can continue to do this. This is called long division, okay? This is called long division. You should know how to do this. So from long division, you can have a fk recover from this coefficient. Remember, long division is, this is an expression of a fz, okay, in here, fz. According to the definition, fz is a definition of fkz minus k, all right? Okay, so that's why you can retrieve the coefficients of fk from these coefficients. Do you see that? But this is tedious. It's very brute force. I hate it. So PSE is not the real way we want to go. We actually want to do PFE, okay? So because we have known that this unit step is this one, now they are using Z minus. But if you do a Z times Z, you can see Z divided by Z minus 1. It's fine, okay? They are the same. And if you have an exponential function, then you end up with this one, okay? And this one. Why this is true? Because if you have TK, T is K times KS, TS is my sampling period. So then this is my K times T is how many ticks, how many periods. So this is the T. So you put this one in, this T, so you have a minus A TS to the power of K, A minus A TS to the power of K, okay? And this is exactly what we learned just now about exponential function. Like we said, oh, A to the power of K, what is the Z transformation of this? Okay. Okay, so, but let's summarize Z transform. Okay, I told you this one slide you have to know. Giving Fz, how you come out of K. The brute force way to do long division, then you can draw this picture. The smarter way is to do PFE, doing a lookup table. Of course, I'll give you a table when we have the exam, okay? Properties as linearity, time shifting, okay? So that's easy to prove, okay? That's easy to prove. Time shifting is interesting. So you have Z K minus 1 according to the definition. So because this is xk minus 1 to the Z minus K according to the definition. So Z minus K keep writing. So here you have when xk is 0, okay, then it's minus 1 is this one. This is K is 0, K is minus 1. So you have all these things here. Okay, okay. But somehow I can pull out Z minus 1, then this term, if I pull out Z minus 1 term, then this is supposed to be Z to the 0, so I need to give a Z1, right? So then I pull out this term, I have Z1 left for this term, okay? Z1 left. The same thing is this. For this term, if I pull out Z, okay, minus 1, what's left is a constant. So then by comparing this one with the definition of my xk, so we get Z minus 1 in here. So in other words, Z minus 1 is an operator. If you operate on xk, okay, is xk minus 1. It's like this is called back shifting, okay? Back shift. So the current is T, the back shift is T minus TS. Or currently you are K, then your back shift is K minus 1. So this is actually called back shifting. Similarly, you can do xk plus 1, okay? But if you k minus k is the same thing like this. So Z operation is some sort of shifting. If it's a negative sign here, it's backwards shifting. If it's positive k, 0 here, then it's called forward shifting. A forward shifting is a k plus k minus 0. Or minus is a k minus k0, okay? So that's called time shifting, So let's do more properties of Z transform. We should have IVT, FVT as well, and we're going to go through some examples. Initial value theorem, final value theorem. I want to draw your attention that in a Z transform, the format is different to the Laplace transform, okay? No, very different. Sometimes people get confused. Say, for example, I have ft and fs, they are Laplace transformation pair. So my final value actually equals what? Equals I send s to 0 and fs. Is this correct? No, don't forget this s, okay? The same thing is true that what is f0? Is you send s to infinity s times fs, okay? I'm sorry, the pen is, but it's already good enough. Let's go through that. So in control system analysis, we usually do not consider things below 0. Okay, so here is called initial condition. So because of you truncate all the past, so then you have a z in here. So therefore, people are curious about what about z minus? Okay, so that's in continuous time domain. We need to talk about initial conditions. But z transform with simply z, initial condition is z. It's 0. It's 0. Don't use to don't use 0 minus like in continuous time domain. So this is also called one-sided. One-sided or unilateral Z transform. Okay. So initial condition meaning this 0 here. Okay. So let's start. How to reflect the initial conditions? Say, so this is my xk. So this is by definition, okay, and this is also definition, okay. The question is here is if I have a shifting here, okay. So remember, this k plus 1 is as if it is derivative. Derivative, okay, as if it is derivative. Because I know that in the derivative, in the continuous time domain, like f dot t, sorry, Laplace transform is s f s minus f 0 minus, right? Here I have something similar here. So, but let's do a definition, okay? So this is my sequence. I just put the sequence in here and the z minus k in here. So this is my sequence. So I keep writing it, I have this one. However, this is not going to be nice because I really need to put in something called shifting, okay? Shifting. That means x1 z minus 1 times z is x1 z0. So this is z0. Then you have x2 here, z minus 2 times the z will get you this one. So, but you have something left over or something added on this on z. Doesn't matter. I minus it here. I minus it here. Okay, so everything is still equivalent to that. Okay, or equivalent to this. Okay. But however, this one can be expressed in terms the x of z, okay? This is x of z defining here. Then you have a z pull out. But remember, you also have a z here, okay? And x0 in here. So that's quite different, Okay, quite different. And remember that in Laplace transform, then you have this is IVT, initial value theorem. But in Z transform, it's different. So given the definition of Z transform, XZ is this consequence, is this sequence, and this one will go to because everything less than 0 is 0, so it doesn't matter. We can still write it from that. So this is the middle one is my initial value. Okay, initial value. So how to make? So what is the x0 in here? Okay, what's the 0 in here? So basically, this is all z to the power of minus. Okay, so and also this is 0. Okay, okay. So I know that I want this one to be 0. Then what do I do? I simply send this z to infinity. Then all these are 0. So this also will be 0. So basically it's x infinity here equals x0. So x0, okay, becomes send z to infinity xz. So this is just xz. There's nothing z or times this. No, just send z to infinity. Okay, infinity. So this is IV. So be careful. This is very different. In continuous time, you need the s. In discrete time, you don't have a z. Okay. So FV that I showed you. This is already I showed you. But what is what about my infinity? Okay, so we do the same here. So let me do z in here. Okay, z in here. So then this is need to be shifted. Okay, the others are the same. Okay, others are the same. Okay, so now this minus this is going to what's going to happen? Is term by term, you are going to have something like this. So you have the same here, same here. In other words, if I send z to 1, and this side will be 0, okay? Will be 0, okay? Send this one to 1, okay? And then we are, so this is just to leave the first and the last, okay? First and last. So the last, this is always 0, we don't care. So the x infinity is, you're sending the z to 1, then this is 1. So then if you add this together, you have first and the last, okay? So you only have this one left. So you basically, you basically send z to 1 in here also. So basically it's z minus 1 xz. You send my z to 1, you are going to get the final value, x infinity, because of this one. Okay, so it's also very different. You have you send z to 1, you have to have z minus 1 in here, okay, times this one. Okay, so let's do a verification, okay? Remember, we did the derivation xz is this one. I want to understand what's the x0, x infinity. So x0 here, initial value. So you send z to infinity. So sending infinity, so this is 1. When final value, you will see you need this term multiplied by this thing here, so that it comes out, you send z to 1, it's still 1. So initial value is 1, final value is also 1, okay? So it's a straight line, okay? Same thing here, and I have z transform of exponential decaying one, a less than 1, remember? So initial value is 1. The reason is, so this is 1. So the reason is you send z to infinity, infinity, infinity. So this is 1. But when you do your final value, you need to z minus 1 multiplied by original xz. Okay, so you send z to 1. Then you will see this is 0. Okay, this is 0. But decays to 0. Okay, to 0. So looks like this is great. Yeah, it is. Okay. So that's initial value, final value theorem. So we are going to now come into something called discrete convolution. I know convolution is very tough. However, if you get a bachelor degree and from mechanical engineering and you cannot tell people what is convolution, that's very shameful. Okay, so you need to overcome this convolution. Okay, let me show you what is convolution. So let's come back. This is a general form of the first order scalar difference equation. So we know alpha, we know beta, I have u in here. So the solution we wrote about this one, okay, there are two parts. One is due to initial state. So I call this is a response of 0 input response. And this whole thing by the derivation is called 0 state feedback. That means when x0 is 0, then the response is only due to the input signals. Okay. Remember, we assume that when when the index less than 0, we always assume it is 0. Okay. So it's very interesting. I need to show you here something. So let's assume that we don't consider this one. We assume this is 0. Okay, 0 initial state. We only focus on that so we can check what's the connection between input and output. Okay, so they are changing xn, doesn't matter. Alpha n minus 1 k minus is the same, right? So by writing that one, I put the u as a uj. So from j from here. Remember previously we put a j in here and doesn't matter, right? So it's the same. Then this one is n minus 1 minus j. So, but this one, this index j plus this index j will be the same as n minus 1, as I pointed to you. Okay. Okay. So now we are using a data array here, uj. So we assume this is called n minus j, n minus j. So n minus j is alpha rn. So hi is I minus 1. So hnj is alpha n minus 1 minus j. Okay. So this hj is something like this. Something like this. So if I draw the alpha is less than 0, then this is something like h. This is hi. This is I. So it's going to be decaying as I. Okay. It's decaying. So later on, you are going to see this H is actually called impulse response. Impulse, because you assume you give the system only an impulse. Okay, then what's the output is this sequence. But I'm going to show you that so this is n minus j. So what is the interesting observation here? Because this index plus this index is n. Okay, it's n. It's a constant. It's constant. So this is actually called, because this can be extended to minus infinity if anything less than 0 is 0. You can pad all the zeros into here, okay? Into here. Okay? And J is changing. J is changing. So this is exactly the discrete convolution. Say for example, basically you have an array. You know, in the computers you have a 1, 2, 3, 4, da 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 da. So you have this is array of U, J. So J is 1, 2, 3. So this is your array, okay, of U, J. So this is another array of HJ. Of HJ, okay, HJ. So this is another array, okay. 1, 2, 3. So these two arrays, how you can convolute them together? Then if you can use this form, that's right. So this is called convolution. Convolution. So it's very interesting. I want to show you something extra. Can you see? I think you can see, right? So let me see. Yeah. Okay, convolution. Hi, convolution. So let me give you an example, okay? Say you have a polynomial px. Let's say this is p0 plus p1 x plus p2 x squared plus pn xn. Okay, so you have another polynomial qx is q0 plus q1 x plus q2 x squared plus this is q, this is n, okay, this is n, this is n, okay, but now I have qm x m, they don't have to be the same. So I want to understand what is the px times qx. Okay, so how to do its coefficients. Okay, how do the coefficients? Okay, I suggest you go to MATLAB. There is a command is called convol. Okay, convol. So you have a convolution of P array. This is called a P array. This is called Q array. Okay. Then you are going to get a C array. This array, okay, array. That C will give you the coefficients of this polynomial. Okay, okay. So go and check it out. Starting from the simplest one, like 1x plus 1x. Okay. So then you will have a convolute of 1, 1, 1, 1. Then you are going to get 1, 2, 1. Okay. But when this is very complicated, how you are going to do that? So in fact, you can use this convolution. So that's one thing I want to show you. You can try any complicated. So this is a P, this is a Q. Okay, this is a P array, this is a Q array. So this is C array. So the second one I'm going to talk about is my professor previously taught me this. So you have a train. So you have a different here, like this 1, 2, 3, 4, 5, da 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 da. So you have a n such train box. Okay. So train box, so this is N. Okay, so in this case, let's say this is called UJ, okay, UJ. So this train is going this way, but there's another train but it's going opposite way. So it has different boxes in here. So 1, 2, 3, 4, 5, 6, until you have different train, okay, in here, okay. But the train is moving this direction, okay. This train is moving this direction, and they start to meet, okay. They start to meet. So this is like an array, okay, like a array of HJ, okay, HJ. But because the J is moving opposite direction, so I'm going to do J minus J, okay? And I'm going to count this one from different side. So I'm going to J from this N minus J, okay? Meaning I go this direction and I renumber it, okay, renumber it. So this is 1, 2, 3, 4, until M, okay, until M. So we're no longer using that one, okay. So then so this is go this way. Oh, I think this should be, sorry, this should be numbered as 1, 2, 3, 4, 5, da, 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 da. So I have the train goes this way and go this way. If they have some overlapping here, okay, okay, then I just count the product of them and put them together. So this one, then you always start to see how many overlapping. The J from 0 overlapping, so now it's 0 overlapping. So then you move here, you have 1 overlapping, then until you have N as 1 overlapping. Then you can keep going, you can keep going, okay. So this one, I hope you start to see, this thing is exactly using the trend to move opposite direction. Then that's the convolution, okay? That's the convolution. So I hope you see that this is J is moving forward, this array is moving forward, but there's a minus J here, so you should move backwards, okay? Backwards. Then you have something to meet, then you multiply them together and adding the line in there. So if they have overlapping 1, so the summation is x1, okay, and so on and so forth. So that's the interpretation of convolution. There are many online animations about convolution or discrete convolution. You can check it out. Okay, so the convolution, the reason we have that one, so remember xn, I said xn was written as sigma j is 0 to n minus 1. So you have h n minus j uj. Okay, so that's what we have seen in here. What we're seeing here, okay. There basically is n minus 1 in here, okay. But on the other hand, x, we have x already. Let's do the sequence xz in here. So I'm going to, this is my definition. So, but I know xk, so this zk is still copy here, zk copy here. Xk is written as this form, but extend this one from minus infinity to positive infinity. And here is a k minus j and j. Okay, so this is my k, okay, according to this k. By doing that, if somehow I can swap this sigma here, this sigma here, so then what I'm going to get? So the k is written in here, okay? K is inside, j is outside. So then I have this thing with me, this thing with me. And this thing with me is, we know minus j is z to the power of j, z to the power of j. I can pull out, it's a constant, okay? Pull out. But hkz minus k is nothing but hz. On the other hand, this guy together is actually uz, okay? So this becomes uz xz. So now you are starting to see an interesting thing. So I can connect my u input z and my output xz, okay? Inside here, I have h of z. So, and h of z in this case is alpha j times beta. So hj. Okay, hj minus 1. Okay, it's fine. So we come out. Yeah, this is the one hg. Okay, hz is a z transform of the sequence. This sequence is quite important. It is actually linked with the two parameters. So this is called impulse response or discrete impulse response. So remember, what is alpha and beta? Is here, alpha and beta. So these coefficients, right? So now we know that hz actually is called a discrete transfer function. Let's talk about it. So we can link the discrete system through the pulse transfer function. Then we can say, hey, you have originally you have a difference equation. You write down this is called ZS, zero state response, all due to inputs. This one actually in the Z transformation domain, it is linked to that. So the H of Z is actually written as this one, and beta is constant. Basically, this is alpha minus 1, so this is Z minus 1 in here, so you have Z alpha K. Then in the end, you have something, so you cancel out that, so you have beta Z minus 1 alpha. So this one also, you can see, so this is H of Z, okay? I can solve this H of Z. But giving U of Z, you will be able to, from here, you will be able to have X of Z is like this, okay? So then it is H of Z, like this. So then this term is H of Z, okay? H of Z. I think this is UZ is lost, UZ here. So let's memorize that. If we do Z transform of output, that is X of Z, Z transform of U of Z, this one is called, the ratio is H of Z, okay? H of Z, you have H of K, okay? You can do long division or you look up table, you can do that. So that sequence is called impulse response sequence, okay? Sequence, okay? Good, so I know it's a little bit too much, but we have learned Laplace transform. This is easy. So let's go with the system here, okay? So we are trying to do, so this is my input, this is my output. I have, so these are this difference equation. Output, input is follow a difference equation. Solving this difference equation is not trivial. Let's try to solve it using a Z transform. So then yk is yz, okay? So constant is not changed. But k plus 1, you got a z here. It's not backward, but forward shift. This is forward shift, okay? So then this is uz, and these are constant, okay? So then we end up a constant, and a z, okay? So that is linking my input and output. So this is called z transfer function, okay? Transfer function, z transfer function. But now, assuming that I have a step input, we know the uz will be written as this one. I have shown that. Insert this one here. So this is my uz. So how to write my yk? Okay, we don't know. So this is a two multiplication in here. I want to split this one into this guy minus this guy, okay, minus this guy. So in here, from this step to this step is called partial fraction expansion, okay, partial fraction expansion, okay. So for this simple case, it's much easier. You can do coefficients to be decided, okay, So, but for the PFE, it's always possible. You can still using a simple idea of copy, okay, copy. So by doing that, this one is a constant, b divided by a. We know this is a constant, and this one is exponential, okay, it's exponential. So that's yk. You put a different case, so then you're so this is your input, okay. This output is something goes to b divided by a, because this is going to go 0 when k is very big. So this is this is a 1, this is b divided by a. When b is not the same as a, then this is not going to be coincide, okay. So that means you can use the simple water tank or temperature control system solving the first order difference equation, okay, using z transform and z transfer function. So let's do something called Pau's transfer function of a differentiator. Say, for example, I have a signal in here, okay? So this signal is called theta. T coming inside in here, you get yt, okay? But inside here, what operation I did is doing a ddt operation. So this is called differentiator. So we know that the differentiator is something like, if in theta s, then I got a y of s. So I want this y of s is a differentiation of this signal. What do you put here? That's your s, right? But I'm curious now, so I have theta k, put it here, you got a yk. So what put it here as a z transfer function, such that this is like a differentiator, this is a differentiator. So there are two things to do, okay? The first thing is, I assume in the continuous time domain, and this is discretized through this way. So theta t plus s. So this is called forward difference. Forward difference. So this t current is t, but I use forward step minus the current one divided by the sampling period. Okay. So then this is my output. So in this case, I can write yk is theta k plus 1 minus theta k divided by t. So this is my discrete relationship in here. But now what I can do, I can write. So this is my difference equation. But I can also write. This is z. Okay, this is z. YZ is theta z. Okay, theta z. This is also theta z, but you have a step in here. So in the end, this one is z minus 1 divided by t. You should put it inside here. That is my, that's my transfer function in z domain. Okay. But you can imagine this is nothing but just z. Is a forward difference. You have this one. But what is a backward difference? Backward difference is different. It's you based on the current theta t minus theta t minus ts. This is backward information. Current minus backward divided by that. So in that case, you can imagine you got 1 minus z minus 1 divided by t. So this one and this one both can be used as this. Okay, both are, in a sense, are correct. If your TS is really small, okay, if it is really small, that difference is also small, okay. So let's try to do integration. We can imagine. So this is the input, theta is the input, y is output, okay. So I can do something like this. So if I give you 1t plus s, then this is 0 to t, t, ts, so you get this one. So it's a integration, okay? So t plus ts can be written, this is yt, okay? So this is yt, and this is this one. But inside t to t plus s is one step. I simply hold this, then we times this. So this is actually, you have learned, you have something like this. So this is my t, this is my t plus s, t plus ts. So this is ts, okay? So you have something here, you have something here. So you can do yt times ts. This is theta t, okay? Okay, theta t. All right, so that is this term, okay? This term. Yeah, you add on top of the y, then you just integration, okay? Your integration, okay? So in this case, so this is YTTS, or you can say, no, actually I want something here. So this will be my area. So that is this term. So this one is called backward, one is forward, okay? So this one is giving you y, z, ys. So this is this term, this is this term, and this is this term. So zy, y, ts. There's another one here is this z is because of this one. So then from in and out point of view, so then this is integration, and this is the same form, but there's a z extra in here. However, if you divided by z, both sides, you end up with this one, this term. I like this better, okay? I like this one better. So both are called integration. So y is the integrate of theta. So theta integration, you get y. But in discrete time, you can put this one as 1 of s or this one as 1 of s. Both are integrations, approximation. So this is more a pictorial view. So how we represent the shaded area. So this is called yeah. So this is this term. Okay. So this is backward. But you can say, oh, I want this one. So this is forward. Okay, forward. So in other words, you are now at k time instant. Okay. Instead of using this lower, so you are using the upper, the next point. Okay. But people may ask, so why not trapezoid? Trapezoid. Okay. So yeah, basically you just using trapezoid. So this one plus this one times this one divided by 2, right? So this one plus this one times this one divided by 2 is that area. Then add on top of previous ones, you will get the current. Next one, okay, next one. So that one will give you. You can imagine what is. So you are going to do yz divided by theta z. So what do you get? You get z minus 1. Okay. Here you are going to have ts divided by 2. So you have z plus 1. Okay. Z plus 1. So that is, or you can write ts divided by 2 is 1 plus z minus 1. 1 minus z minus 1. So these are the same, right? So this is called bilinear transform. Bilinear formula. Okay, by all bilinear formula. But in MATLAB, in many places, this is also called testing transform. In other words, people may say, oh, you have a 1 of s, okay? What is your z? You can say, oh, this is a 1 over, or can go back, okay? 1 over z minus 1 ts. You can say, oh, it could be ts 1 minus z minus 1, okay? So that's this equation, okay? Or this testing equation. So this is integration can be represented in terms of z. So this is also called bilinear relationship. Okay. So let's summarize what we have learned so far. Okay, I know it's very intense today. I never stopped talking, but let me summarize. We talked about differential equation. We talked about z transform. We talked about one-sided and one-sided. Talk about the inverse z transform, and we talk the properties like IVT, FVT, and zero initial conditions. No, not a zero. just initial condition problem, okay? Then we talk about Pau's transfer function, and we're going to talk about this one later, but not today, okay, not today. But most importantly, we talk about discrete convolution, and we said like 2 Pau's train. So you have a UJ, UJ, and here you have H n minus J. So here you have J is 0 to n minus 1. You're going to have Xn, okay? Xn. So you can see give one, give a 1, then you have 1 minus J. So 1 is minus J, 1 is J. Okay, but remember anything less than 0 is 0, okay? So it's like, because this 1 is a positive J, 1 is negative J. So that's why I use the 2 trains on opposite direction. They meet, then depending on how much overlapping, okay? Overlapping 0, overlapping 1, overlapping 2, and overlapping 3. So all this overlapping will be added together, okay? Add together. Then giving this one as Xn when you have, this is a n is, if you say n is 0, then it's a totally opposite direction. You number that. If you have n is 1, then you have 1 minus j. So the numbering is different. And I told you that this idea, okay, this convolution idea can be used for a polynomial product to get this coefficients. I suggest you try it, okay? And in my lab, help what's the convolution means. And today we also talked about digital differentiation and integration is S and 1 of S, okay? And the corresponding Z transform on a different approximation formula like forward, backward, and trapezoid. Talk about Tustin transform, also known as bilinear transform. So I think we are equipped with all the necessary necessary knowledge that we can, next time we'll talk about sampling theorem and stability issues, okay? So we already got a taste of sampling, meaning if you sample too slow, you will mess up your system. Your system could be unstable, it blow up, right? So next time, we are going to have very solid derivation of the sampling theorem, okay? And this part is very important, so don't miss it. As you can see that I'm writing on the slides, I hope this development of the concepts is useful for everyone. So let me see if I can have some questions from the class or what to do. Where is it? Do you guys have any questions? You can turn on and direct talk to me right now. Kind of lost. Let me see. I'm going to stop sharing. I can see. You're all here. Okay. Yes, yes. Today I have 26 people online, including myself. So 25. That means I have 15 missing. It's fine. Okay, you can watch it later. I know it's very difficult time right now. Everybody stay at home, and you may have conflicting like myself. I have conflicting of schedules. Like my sons may have class right now, and let me see the chat box. Oh, David and Stephen, thank you, both of you, to alert me about sharing the screen. Thank you. If I don't have any question from you, I'm going to end, and I'll meet you again on Friday. So this is Thursday. So I'm going to give out another homework for you, focusing on digital control and practice your Z transform concepts. So,
Professor?
yes, David.
I was hoping to ask, so since we're submitting our midterm today, when will be the earliest we could get our results from it?
That's a very good question. I haven't checked my TAs, and I think you should give them a week. Okay.
Okay.
If anybody very worried about the scores and grades, raise that concern and discuss with me and TA to see where you can get more back to balance out. I haven't finally decided whether we should do pass or fail grading. I was advised that if the course is a core required course, it's better to go with letter grades. On the other hand, if it is not a core required course, like Mechatronics, this course, they allow us to choose to do pass fail option, or grade, or we can still stick with grading a letter grade. So for that, I haven't decided. Somebody said graduating pass new pass option can help. Yeah, well, listen, I'm open to all the options. So, but don't worry, even if we do pass new pass option and you feel like this is not fair to your efforts you put in, you deserve A+. In that sense, I can still help you. You can ask me to write you a great a recommendation letter for your job hunting or graduate school or whatever. So I can tell them, actually, you deserve A+, but due to the virus, we only gave pass, no pass. Okay, so I have to say goodbye. I got another meeting set up. Okay, 3, 2, 1, end meeting.